Hello, welcome to Basics of Finite Element Analysis. Today is the fourth day of this current week, and we will continue our discussion on reduced integration element, and specifically we will actually conduct an exercise and see how this reduced integration exercise is actually performed. So, in one of our earlier classes, we had seen that the weak form of the two equilibrium equations are given here. Okay. And using these weak forms and these interpolation functions, we will now develop the stiffness matrices for the entire system. So that is what we will do. We will start with the first equation. So, corresponding to the first equation, we get integral 0 to h e d alpha I over dx bar d alpha j over dx bar g a k s dx bar, and then this entire thing is multiplied by this unknown constant, and I have to sum this up on j is equal to 1 to m. Okay. So, plus sum on j is equal to 1 to n s j. So, wherever we had psi's, we are replacing them by s times betas, and wherever we had w's, we are replacing that by alpha times w's, right. So, that is why we are getting here the index of we are adding from 1 to m, and in the second case we are adding from 1 to n. Okay. 0 to h e t alpha I over dx beta j g a k s dx bar. The other thing is the first equation, equilibrium equation, was multiplied by weight function W1, and here we assume that weight function W1 is same as alpha I. So, that is why we are getting this alpha I here. Okay. So, this equals integral of alpha I f dx bar plus the boundary terms alpha I evaluated at 0 q1e plus alpha I evaluated at h e times q3e. Okay. So, that is my first equation. The second equation is again j is equal to 1 to m w j 0 to h e, and here the whole equation is being multiplied by weight function W2, which is beta. So, I am multiplying the whole equation by beta I d alpha j dx bar g a k s dx bar plus j is equal to 1 to n s j 0 to h e d beta I over dx d beta j over dx, and it should be actually x bar times E I, and this entire thing is in brackets, plus beta I beta j g a k x equals beta I evaluated at 0 Q2E plus beta I evaluated at HE times Q for E. Now, couple of comments. Here Wj is present and Sj is present in the first equation, and also Wj and Sj is also present in the second equation. Wj and Sj are constants of associated with W and psi, and they are unknowns. So, we have to find them out, right. And specifically physically they mean the displacement at node 1, deflection at node 1 will be W1, deflection at node 2 will be W2, right. Similarly, rotation at node 1 will be S1 and rotation at node 2 will be S2. So, these are two equations, and in W's and S these are two equations which are linear. They are linear equations because the powers of W's and S are 1, and these are coupled equations. So, I cannot, so these are simultaneous equations in W and S. So, from here I can compress all this as K I j 1 1 W j plus K I j 1 2 S j is equal to F I 1. Okay. So, this is the equation I get. So, this is equation 1, this is equation 2, this is the thing which I get from E 1, and what is the definition of K 1 1, I will explain that. So, please bear with me. And here I am adding these K I j 2 1 W j plus K I j 2 2 S j equals F I 2. Where, so this is E 2, and now I will define K I j 1 1 equals this term, then my this is K 1 2 j. Okay. This is K 2 1 j, K 2 1 I j. And finally, I have K 2 2, this entire thing. So, if I have a node, an element with two nodes, node 1 and node 2, let us say the element is He long, then I will get essentially two equations from the first weak form E1. How do I get two equations? When I in first case I put alpha I give I as the value, I give the value of I is 1 and I get one equation. Okay. Then I give the second value, I is equal to 2, I get the second equation. Okay. Similarly, I get two equilibrium equations from the second weak form E2. Here also beta I is the weight function. So, I give two betas. In first case I give beta 1 and in the second case I give beta 2. So, I get two equations. So, overall these are four equations, right. These are overall four equations associated with two nodes of an element which is He long. Now, we have talked about reduced integration. So, what we note is that when we are integrating this function, the function which is underlined in green, we do not do reduced integration. If m, so here we have deliberately specified m and n as different. Now, if m is equal to n is equal to 2, then we will have four equations which we talked about, right. We will have four equations and we will still have two nodes. So, there will not be any problem. Well, now to avoid shear locking problem, we will go on each of these terms and we will figure out which term has to be done using reduced integration method and which terms when we integrate we do it without reduced integration. When we look at this term in green which is represented by K11, we do not do reduced integration on that. The terms which are underlined in purple, which is K12 and K22, they also do not go through reduced integration. The term which is underlined in light blue, we look at this place. So, here we have two terms. The first term is d beta I over dx, d beta j over dx times Ei, and the second one is beta I beta j times Ga Ks, right. This term, so this term which is underlined with two lines, this we do not do reduced integration, normal integration. Okay. Because if we did reduced, then if m was 2, then again we will have the same thing, same problem. And here when we are evaluating this beta I times beta j, this is the term which we do reduced integration. And once we do that, we eliminate that shear locking problem and we get our solutions. Some other points, we see that, so K11 is a, okay, so before I do that, I will write down the overall system of equations. So, the overall system of equations looks something like this. So, here we have this K11 submatrix. Here I have K12 submatrix, K21 submatrix and K22 submatrix. Each of these submatrices is 2 by 2, because I and j can take at the most two values, right, for m is equal to n is equal to 2. So, K11 is 2 by 2, K12 is 2 by 2 and so on and so forth. So, the overall stiffness matrix is 4 by 4 and it boils down to the same thing because we have 4 equations. So, we should have a 4 by 4 matrix. In the unknown vector, we have W1 and then W2, S1 and S2. Okay. And on the force side, we have F1 and F2 and 0 and 0. So, this is the external force which is being applied, and plus if there are some point forces, they are Q1, Q3, Q2 and Q4, and all these equations are at element level. All these equations are at element level. Now, when you see this equation, this over 4 by 4 system, you note that K11, so now let us look at, so first just see this, so we have 4 sub matrices K11, K12, K21, K22, okay. Now we will look at K11. So K11 is symmetric in I and J, which means this submatrix is symmetric in I and J, okay. Now we look at K22, this is also symmetric in I and J, okay. Does not matter whether it is I equals J or J equals I, we will get the same answer. So the other diagonal submatrix, which is K22, is also symmetric. For this overall matrix to be symmetric, now what we want is that K12 should be transpose of K21, then the overall matrix will be symmetric. So let us see whether that is the case or not. So here we see that K12 is d alpha I over dx bar GAKS beta j integral, and K21 is beta I GAKS, and this should be j times dx. So the definition of K12 and K21 is such that these submatrices are also, they are not symmetric in themselves, but this submatrix is transpose of this submatrix. So the overall K matrix is symmetric. Okay. So once again our weak formulation, and this submatrix, this is something we saw also in our earlier formulations, that if the system was conservative and if the system could be represented as a functional, as a bilinear functional, then whatever we will get out will be something of this nature. So we have a symmetric matrix, and the way we, so we can compute each element of these of this symmetric matrix, and then we find, so this is element level equation, and then the next step is that if we have broken our beam into n number of elements, so we write such n such set of equations, assemble them using conditions of continuity and force equilibrium, and then impose the boundary conditions to get a reduced set of equations and solve them to get our solution. So this completes our treatment of the shear deformable beam, which is also known as the Timoshenko beam. And in this treatment, we have learned we have learned several things. One is, how do we handle equations, handle more than one differential equations if they are coupled. They may be linear, but they are coupled equations. So that is what we saw in this case, that psi and w were appearing in both the differential equations, and we could construct a weak form, and from that we were able to develop a set of equations which could be used to solve these unknowns. So that is first thing. The second thing which we learnt through this exercise is that if one particular variable requires that its interpolation function should be one level higher than the other one, then we can address that requirement either using the consistent interpolation element method, where m was defined as n plus 1, or the other one was where m equals n, but we still take care of the differentiability requirement by using a reduced integration method. We will learn more about this reduced integration method in the next week when we deal with numerical integration procedures, because in computer implementation of finite element analysis, we do not actually go around analytically integrating all the functions, but rather we use some fast numerical procedures to integrate these functions. So, we will learn more about that, and then we will see how we can use reduced integration approaches to address these kind of problems. So, this is pretty much what I wanted to cover in context of Timoshenko beams, and in the next class or in next school classes we will discuss eigenvalue problems. So, that completes our discussion for today, and we will meet tomorrow. Thank you.